Good evening, everyone. So, it's the first day back from spring break, and probably having another test in this class again, so I'm just going to go over the notes that the professor gave again. These are going to be just the slides that had that icon, and this is going to be the chapter on polysaccharides in microbiology. So, polysaccharides are made extracellularly by microorganisms for food. You could also have them in the pharmaceutical industry as well as the usage in vaccines. Again, extracellular. These are extracellular products. You have several uses, such as binders, coagulants, emulsifiers, film formers, gelling, lubricants, stabilizers, thickening, and suspension. So I just listed a few of them there. Okay, so extracellular polymers are going to be our polysaccharides. Most bacteria, under the correct conditions, will make these polysaccharides of these high molecular weight mucoid substances. These could be in the form of the slime layers, the capsules, and the sheaths. Most are composed of polysaccharides, and they're also going to be strain specific. That's also a good point to make here. The creation of these mucoid substances will allow the bacteria to form biofilms and evade the immune system that may have developed to earlier infections. Okay, so building blocks of polysaccharides. So they're going to be water-soluble bipolymers. They're going to be made from the simple building blocks, and these are also going to be similar too. You have a pyranose, which is a 6-carbon ring. That's going to be an example of glucose. A furanose will be a 5-carbon ring. An example of a furanose would be fructose. More on the structure, we have these glycosidic bonds between the monosaccharides. They're going to be between the hydroxyls and the anomeric carbons. And an anomer is going to be the geometric variation at certain atoms in the carbs, while an epimer is going to be a stereoisomer that differs in configuration at any single stereogenic center. So anomer is going to be a geometric variation found at certain atoms in the carb, while the epimer is a stereoisomer that differs in configuration at any single stereogenic center. Again, these glycosidic bonds are going to be between the anomeric carbon and the hydroxyl, another hydroxyl and the other anomeric carbon. Polysaccharides also have primary and secondary structure. So primary structure would be the identity sequence, or the linkage and the anomeric sequences of the monosaccharide residues. So this is going to be like the actual sugar units that make up this polysaccharide. The secondary structure, however, it's going to be also have the relative orientations around the glycosidic bonds. And you're going to have these rotation angles. They're going to be limited by steric constraints, though. An example would be dextrin. This is a polysaccharide that's composed of glucose at 1,6-glucoside bonds. So there's a specific type of bond they are made, 1 to 6. More on the structure. So, let's see. Primary, again, it's just the repeated and stiff units. And you could also have these coils, too. Crumpled ribbons are another thing. They're going to be for 1,6. And these could make random coils. The 1 to 6 linked polysaccharides make these random coils. For charged polysaccharides, however, you're going to have this interaction between ions. So in alginate, calcium will interact with polyglurinate, leading to a gel network. So in alginate, the calcium will interact with this other molecule here, the polyglurinate, and you're going to make this gel. Let's talk about the specific production of one of these polysaccharides, xanthan. So xanthan gum It's going to be found in baked goods, sauces, dairy, gelatin, pills, synthetic saliva, gluten-free foods, and thickened foods. You're going to have this specific structure in the polysaccharide. Xanthan has these beta-1,4 linked glucose backbones. And at the third position, you're going to have an alternating glucose monomer with a side chain of 1 glucuronic acid and 2 mannose residues. On the non-terminal D-mannose, this D-mannose will carry an acetyl group at the 6th position, so that's on the non-terminal D-mannose. A pyruvate is attached to the terminal mannose, however, so you have a pyruvate. The number of pyruvates and the molecular weight determines the viscosity of xanthan. Let's talk about the organism now that makes the xanthan gum. This is going to be Xanthomonas campestris. So Xanthomonas, again, that implies it has to do something with xanthan gum. And the species name is campestris. This is a gram-negative rod. It has this yellow pigment that makes it's a plant pathogen as well. The medium for this fermentation will be 4 to 5% carbohydrate. You're going to use glucose, sucrose, and this corn hydrolysate. You need 0.05 to 0.01% nitrogen. And again, you need this for the proteins. You could get the nitrogen from yeast extract, peptone, ammonium nitrate, and you also need some salts. So we have some conditions to follow as well. So it's going to be a 2-day batch fermentation. The pH is controlled at 7 because if you drop below 5, this is going to stop the production. So you need some NaOH to keep it at 7. And the temperature is 28 degrees. Let's talk about recovery. So we're going to go to the end here with xanthan. And recovery will stop, or the fermentation will stop when carbs are exhausted. When you run out of carbohydrate nutrient, the fermentation, of course, will stop. The broth is pasteurized by heating or boiling to kill the Xanthomonas campestris. Xanthan is now precipitated. You're going to be using methanol or isopropanol, so 2 types of alcohols that you're going to use to precipitate. Then you dry and mill your xanthan gum. 2 other polysaccharides. So we have alginate. We brought up alginate earlier. This was the one that was a charged polysaccharide, and then you had the calcium ions, and remember that gluconate, or whatever it was called. Sorry about that. Let me go back. The polygluconate, I can't tell if I wrote that incorrectly. I probably did. But remember, you have the calcium in that polygluconate, or whatever it's called, and that forms a gel network because alginate is charged. Right, so alginate is made by Pseudomonas aeruginosa. It's also made by Azotobacter vinlandi. Azotobacter, that's interesting. Okay, so this is a linear polysaccharide of these homopolymeric blocks of D-mannurate and alpha-L-gluranate. And this is going to be used for immobilizing microbes on the ion exchange agent, as an ion exchange agent, I should say. We also have scleroglucan, and this is made by the sclerotin fungus. This is a beta-glucan, so the linear chain is beta-delta-1,3 glucopyranosyl units with a beta-delta glucopyranose every 3rd unit. It's going to be used in skincare lotions, sun protection, shower gels, makeup, mascaras, shampoos, shaving foam, and thickening drilling muds. Alright, those are all the notes that were given the icon for polysaccharides. Please do something nice for someone, and good night.